In this video, we're going to talk about taking derivatives of derivatives. So remember that the first derivative, talks about at what rate the function is changing. But we might want to know at what rate the rate of change is changing. So we can investigate that by taking the derivative of the derivative. So the derivative of a function is also a function. So we can take its derivative. So if we take a derivative of a derivative, you get the second derivative. You can continue taking derivatives. So if you take the derivative of the second derivative, you get the third derivative, and so on. So the notation we use, so given a differentiable function, y equals f of x, the second derivative of the function, we could write as y double prime, so y prime prime, or you could write it f double prime of x. Okay, so we say this y double prime, okay, or f double prime of x, okay. Or, using the Leibniz notation, the dy by dx, it looks like d squared y over dx squared. Okay, so this is the derivative of y twice, both with respect to x. Both with respect to x. Both times. So it might look a bit weird. So the square goes on the d here because you're taking the derivative of y, okay, twice. The reason why we have dx, the square, also down here is because, like I said, in other calculus classes that are more advanced, it's possible that you have multiple variables, and you might want to take one derivative with respect to x and maybe one derivative with respect to z. Okay, so you want a way to indicate that. In our class, though, we're only going to ever be doing the same variable, so that's why the square will be on the x here. Okay, so it's always the same variable taken again. The other one, I guess, that we had that you might see is d sub x, and we just put a square up here for the second derivative, okay? And then you would say of f of x. That's less common. The first three you should be comfortable with. Now, you can also take further derivatives, okay? So the third derivative we might write as y triple prime, okay? Or f triple prime of x, or d cubed y over dx cubed. Okay, so this would be all the third derivative. Okay, now after the third derivative, we start doing numbers. Okay, so not to confuse it with a y to the power 4, okay, we put it in brackets. Okay, so this is the fourth derivative, or you might say f with a 4 there in brackets x. And the Leibniz notation one looks the same, so I'm going to stop writing it. So the fifth derivative, again, we use the brackets, so it's y to the 5, or f to the power 5 of x, etc. Okay, so this is the fourth derivative. Okay, and the fifth derivative, and it just continues like that. So the third one is when we stop doing the dashes, okay, because they just get too many. So let's do an example. So let's determine the fifth derivative of this equation, and we also want f double prime of negative 1. Okay, so we have f of x, so we're going to take its first derivative. Okay, this is just a polynomial, so we can just use the power rule for each of the terms. So the first derivative is going to be 4x cubed minus 3x squared plus 8x. And then the 17 is a plus 0. Okay, so we don't need that. So then I take the second derivative. Okay, and now I'm taking the derivative of the derivative. So I'm looking at this equation here. And again, it's a polynomial. I just need the power rule. So now it's going to be 12x squared minus 6x plus 8. Okay, now I want the third derivative. So f triple prime of x. Okay, so this is going to be 24x minus 6. So I just took the derivative of that one. Now the fourth derivative is just 24. And then so the fifth derivative is just 0. And in fact, all derivatives, if I keep taking derivatives, they're just 0 from now on. Okay, so those are the first 5 derivatives. Now we also wanted f double prime of -1. So I take the second derivative and I plug in -1 for x. So I'm going to have 12 plus 6 plus 8. So I get 26 for my second derivative at -1. Okay, so it's just like normal, but you can just keep taking derivatives on top of derivatives. Let's do a couple more. So here we only want the second derivative for each of these functions. Okay, so f of x is x cubed minus 2 to the power 4. Okay, so we're going to want to use the chain rule here. So to do the first derivative, okay, so I have something to the power 4. I don't want to really expand it because the 4 is just too much to do. So I just want to use the chain rule. So it's like u to the power 4. So it's going to be 4u to the power 3. So 4x cubed minus 2 to the power 3. But then I need to remember to multiply by the derivative of the inside, which is 3x squared plus minus 0. Okay, so that's the derivative. If I rewrite this, it's going to be 12x squared times x cubed minus 2 cubed. Okay, so this part is the outer derivative, using the chain rule, and this part is the inner derivative. Okay, now I want to take the derivative again because I want the second derivative. So I want to do f double prime of x. Okay, so I'm using my simplified form, but I see that I have x's times x's. Okay, so for the second derivative, I'm going to need the product rule. Okay, so I do the derivative of the first one. So the derivative of 12x squared times the second one, x cubed minus 2 cubed, plus the derivative of the second one times the first one as it is. Okay, so this is going to be 24x times x cubed minus 2 all cubed, plus, now I need the chain rule again, so it's going to be 3x cubed minus 2 squared times the derivative of the inside, which is still 3x squared, times the 12x squared on the outside. Okay, now simplifying, so I can take out 12x and then x cubed minus 2 squared. Okay, that's going to make things a little bit easier for me. So maybe I'll just highlight this a bit. So the 12x, I see it's in here and also in here. Okay, and then this part, the x cubed minus 2, I see is here and here. Okay, so those things I'm going to pull out. They're in both terms. So the leftover part from the first term is just going to be a 2, and then one more x cubed minus 2. And then from the second part, I'm going to have 9, and I'm going to have x cubed because there's 4 x's in total, and I took one of them out. And then all of those x cubed minus 2's go away, so I think it's just that, actually. And then if we open up the brackets, I'm going to have 2x cubed plus 9x cubed. That's going to be 11x cubed minus 4. So this would be my final second derivative in a simplified form. Okay, so another one. So again, here right away, we need the product rule because I have x's times x's. So when I do my first derivative, g prime of x, I'm going to do the derivative of 6x, which is 6 times ln of 2x, plus the derivative of ln of 2x, which is 1 over 2x times 2, so that's the derivative of the inside, times my 6x. Okay, now if I simplify this, I get 6 ln of 2x plus, and now these x's cancel, the 2's cancel, so it's just plus 6. Okay, so now when I do my second derivative, notice that it got easier this time. So I don't have any more product rule. Okay, this is just a number times something to do with x's. So I can take the derivative right away. Let's pull the number out. Derivative of ln 2x, we already said, is 1 over 2x times 2. The derivative of 6 is 0, so that's gone. Okay, the 2's cancel out. The 0 doesn't matter, so I get g prime of x is just 6 over x as my final answer. Now, something neat about the second derivative, so if my function s of t represents the position of an object, then we know the first derivative gives the velocity of the object. Okay, so we call that v of t, right? So that's s prime of t when we take the first derivative. So it's like the speed, but it can be negative, right? So it's not exactly the speed. That's what velocity is. So if we differentiate this derivative, so we take the derivative of the velocity, what we get is the acceleration of the object. Okay, so we get the acceleration. Now, like I said, the signs on these give you more information. So this is true also for the second derivative, or the acceleration. So when the first derivative is positive, the object is traveling sort of whatever forwards means. Okay, so in the right direction. But when it's negative, it's going backwards. Okay, so the opposite of however it's defined. So now if we take this further, the acceleration actually depends on, the interpretation depends on the velocity as well. So if your velocity is positive and the acceleration is positive, that means that, so you're moving forward, but the acceleration is positive means that the velocity is also increasing. So it's getting faster, essentially. So when they're both positive, you actually get that you're speeding up. So the object is speeding up, okay, and going forwards because it's positive. Okay, but when the acceleration is negative, that means that the rate of change of the velocity is getting smaller, so it's decreasing. So that means that your speed, okay, so not the velocity, but sort of the absolute value of the velocity, is approaching 0. So it's getting closer to 0. So this, you would say, you're slowing down. So because the velocity is positive, you're still moving forwards, okay, but you're not speeding up, you're actually slowing down because the rate of change of your velocity is decreasing. Okay, so that means that the number associated with your velocity is getting smaller. If the velocity is negative and your acceleration is positive, so negative means you're moving backwards. So if your acceleration, so this one is a little bit confusing, I find anyway. So when you say, so you would think the acceleration is getting positive, you would think you're speeding up. But what it means, so the rate of change of the velocity is getting bigger. Okay, so when your velocity is negative, getting bigger actually means that you're getting closer to positive. So if you think about the speed, the speed is actually getting smaller because we're getting closer to 0. So here we're actually going to be slowing down. Because our velocity is negative, when it gets bigger, it actually gets closer to 0, which means the numbers themselves are getting sort of smaller. The absolute value is getting smaller. So we're slowing down, but moving backwards. Okay, so it's when the acceleration is negative here, that's when we speed up. Okay, but we're going backwards in both cases. Okay, so notice when they're the same. Okay, so maybe I'll just write. So these two are the same and those two are the same. So when they're the same sign, that's when you speed up. Okay, it's the same sign. Yeah. When they're both positive or both negative, that's when you're speeding up. If they're different, that's when you're slowing down. Okay, so let's do an example. So a car is moving in a straight line with position from the starting point given by this equation. Okay, so the velocity, v of t, is the derivative of the position. Okay, so we just take this equation and take its derivative. So it's going to be 3t squared minus 4t minus 7. Okay, now if I want the acceleration, I take this equation and take its derivative. So a of t is normally what we use for acceleration. This is the derivative of the velocity, which means it's the second derivative of the position. Okay, so it's going to be 6t minus 4. So, on what time intervals is the car moving forwards or backwards? Okay, so forwards and backwards. Here we want to know where is v of t, the velocity, positive or negative, right? Because the sign of the velocity tells us which direction we're moving. So we don't care about the acceleration at all. We just want to know where the velocity is positive or negative. So to solve this, what we want to first find is we want t so that the velocity of t, the velocity at t is equal to 0. So why do I want it at 0? So the idea is, in order to switch from positive to negative or negative to positive, I have to go through a 0. Okay, unless there's a point where the velocity doesn't exist. But here it's a polynomial, so it exists always. So I want to find all the places where it's 0 because that's where it could switch. Okay, so that's what I want to do first. So our velocity was 3t squared minus 4t minus 7. So I want to know for what t values is that 0. So that means I want to factor this polynomial. So we have to use the sort of over-the-hill method. Okay, so I want to factor, I want two numbers that multiply to give negative 21 and add to give negative 4. Okay, so they multiply to give these two times together, add to give this middle one. So in fact, I think that's going to be 7 and 3 because it's negative, it's going to be negative 7, positive 3. So we use those numbers and we rewrite our polynomial. So I'm going to split this middle term. So it's 3t squared plus 3t minus 7t minus 7. Okay, so I just took a negative 4t and I split it into two terms. Okay, now we do our factor by grouping. So we group the first two, group the second two. So I can pull out 3t from the first two, and I'm left with t plus 1. And I can pull out a negative 7 from the second two, and I'm left with t plus 1. So now I can pull out my t plus 1. And I'm left with 3t minus 7. So I have it factored now. So this is equal to 0 when one of these terms is equal to 0. So that means t plus 1 is 0, or 3t minus 7 is 0. So I get t is negative 1, or t is 7/3. Okay. Now this one I can just immediately get rid of. So why is that? Well, t is time. Okay, so this we would say is not in the domain, even though the domain wasn't given, but in context of the problem, there's no negative time. Okay, so we can't go back in time. So we never want negative time values. Okay, so there's only one possible place where it could change. So then what we can do is, one way to do this is to make a number line. Okay, and I'm going to put 7/3 on here. Okay, so at 7/3, v of t is equal to 0. Okay, what happens, I started at 0 just because this is not in the domain here. So what happens is on each side of 7/3, the velocity is either entirely positive or entirely negative. Okay, so 7/3 is where it's actually 0. So that's the only place where it can change from positive to negative. So it could be that it's positive on both sides, but it might be that it switches there. So the way we can check is we can just evaluate at a point. Okay, so 7/3 is like 2 point something, so let's try t equals 1. So if I do v of 1, that's going to be 3 times 1 squared minus 4 times 1 minus 7. I don't actually care what this number is, but if we compute it, it looks like it's going to be minus 8. Okay, so it's negative. So that means on this interval, v of t is always negative. Okay, so then we could try something bigger than 7/3. Okay, maybe t equals 3. So if I put in v of 3, now I use this one for the 1. It doesn't matter. I actually prefer using the factored form, so I'm going to do that this time. So this is going to be 3 plus 1 times 3 times 3 minus 7. Okay, so this is actually 4 times 2, so 9 minus 7. So I get positive 8, so it's positive. So that means on this interval, it's always positive. So v of t is always positive when the time is bigger than 7/3. So to answer the question, we're going to be moving backwards on the interval when t is, when t is between 0 and 7/3. Okay, and then we're going to move forwards. Okay, so this is for from 7/3 until infinity, essentially. Okay, because it didn't tell us how long this model makes sense. Okay, so we're moving. So you think about it as backing out of like a parking spot. So you back out, and then you move forward. Okay, so that's the idea. So those are our intervals. Now it wants to know what time intervals are we speeding up and what time intervals are we slowing down. So here we want to compare. Okay, so speeding up or slowing down, we want to compare the signs of v of t and a of t. Okay, so if they're the same sign, then it's speeding up, and if they're different signs, then it's slowing down. So, to do that, I'm going to make a table first. So I'm just going to redo our table for v of t. Okay, so let's just go like this. I'm going to put 7/3 over here. This is 0. Okay, so then I have v of t. It could, maybe I'll do this in a different color actually. Let's do it in blue. Okay, so v of t, this is where it's 0. Okay, on the first interval it was negative, and on the second interval it was positive. Okay, so that's where v of t is positive and negative. Now if we want to figure out for the acceleration, okay, so let's remember a of t was 6t minus 4. So using the same idea, if we want to know where it's positive and where it's negative, we're going to find where it's 0. Okay, so we want to set a of t equal to 0. So that's 6t minus 4 equals 0. And if we solve, we get t equals 2/3. So 2/3 is less than 7/3. Okay, so I'm going to just add it into our table. Okay, now this is where the acceleration is 0. Okay, so now I'm going to do another row for the acceleration. Okay, so this is the only place where the acceleration can change. Similarly, I know because the velocity, I'm just going to fix my table a bit. Because the velocity is negative whenever I'm less than 7/3, I know it's negative in this interval between 2/3 and 7/3, and also negative in the interval between 0 and 2/3. Okay, now for the acceleration, I want to check a point. So something that's less than 2/3, maybe I want to check 1/2. Okay, so a of 1/2 is going to be 6 times 1/2 minus 4. So that's 3 minus 4. This is -1. So that means that it's negative in this interval. Okay, now I want to check something bigger than 2/3. Okay, I don't have to check in every interval, but I'm going to pick something in this interval here. Maybe I check 1. So that's 6 times 1, minus 4. So that's 2. So this is a positive number. Okay, so I know that this is positive. If you want to check something bigger than 7/3, you can, but I actually know this is positive because this 2/3 is the only place where the a of t can change. Okay, so it did change, in fact, but these two have to be the same because it cannot change at 7/3. Okay, so here's all my intervals, so now it's easy to compare. Okay, so I see on the interval from 0 to 2/3, both are negative. Okay, from 2/3 to 7/3, they're different signs. And then bigger than 7/3, they're both the same sign again. So now I can answer my question because I can say that we speed up, okay, on the interval, so from 0 to 2/3, and then again from 7/3 to infinity. Okay, now I'm just going to make a note here. So in this interval, because they're both negative, we're speeding up, but we're going backwards. Okay, but in this interval, we're speeding up in the forward direction. Okay, and then we slow down on the interval from 2/3 to 7/3. Okay, and again, we're going backwards on this interval. Okay, so this also makes sense if you think about backing out of a parking spot. So you're first stopped. So you start accelerating, so you're speeding up to get out of your spot. Okay, and then once you decide you're out, you start slowing down so that you can change direction. Okay, so you have to slow down to a stop, and then you can move forward, and then you're going to speed up again. Okay, so that's sort of what's happening here. But in order to compare, in order to know whether you're speeding up or slowing down, so maybe I should just write here. So this is when they have the same sign. Okay, and this is when they have different signs.